Not many Platter Day fans in here. There's only a few of us with plaid on. It's Platter Day. There's got to be a party out there tonight, a Platter Day party. Come on. Oh, yeah. That was yesterday, right? Science on Tap. All right, I sent out an email announcement, exam next Friday. Okay. So I think I put on there that the light, there's nothing on there from the light reaction stuff. So look in the announcement on EDUCAT. I believe when I make an announcement in EDUCAT, it also goes into your email. So you get it twice. So I try to remember to do that. So it will start with the phloem translocation information and go through the biological nitrogen fixation. But we'll leave the light reaction slide set for exam 3. Okay. All right. So I think we left off here, looking at the idea that when you peer into an actual chloroplast and look at the thylakoid membrane, the big transmembrane complexes that are playing part of the game of the light reaction process, you can see that they're not this evenly exact lineup of everything in order. So what that means is that you need mobile carriers in order to deliver electrons to these bigger complexes. And so we will be thinking about those players as well as these massive transmembrane complexes. By the way, the LHC1, LHC2, those are special antenna complexes. They're called light harvesting complex 1, light harvesting complex 2, and they're basically just beefed up antenna complexes that we've already mentioned. You tend to find those extra complexes in plants that are shade tolerant. So the ones that are okay with partial or mostly shady conditions, they usually have beefed up antenna systems. And so they gave them special names, the LHC1, LHC2, and they associate with different photosystems. So the 1 means it's associating with photosystem 1. Okay. For those of you who have taken any kind of cell and molecular, that might look vaguely familiar, looking at the protein shapes and configuration. Again, this is the thylakoid membrane that you're looking at, and then photosystem 2, photosystem 1, and then the cytochrome B6F and the ATP synthase. So again, just trying to point out that these are really large complexes that span the entire width. All right, so they're pretty much fixed in place. They're not going to be moving around in any way laterally through the membrane. So that means we need mobile carriers to start carrying electrons from one transmembrane complex to another. So again, with those antenna systems, they tend to associate with these photosystems, photosystem 1 and 2. And again, that's what they see happening in those antenna complexes is all inductive resonance, where you just have energy transfer, not electron transfer. But their job is to deliver that energy into the reaction center of the two photosystems. All right, so there's a reaction center in photosystem 1 and photosystem 2. So these light harvesting complexes are the ones that they see them beefed up in the shade tolerant plants. The light harvesting complexes. So they give them special names because they find that in the shade tolerant plants, they're a little bit more intricate and just more of the antenna pigments. So again, you've seen this already, just looking at the idea that these antenna pigments surrounding the photosystems are capturing wavelengths of light, slightly different wavelengths of light. And then they're doing an energy transfer process. And we often say funneling. Figure A actually looks like a funnel. The energy gets funneled into the reaction center. So we tend to use that terminology. Here, this is what they figured out of the light harvesting complex 2 that associates with photosystem 2. Again, just trying to demonstrate that it's complex, it's big, lots of components to it. Okay, this next image we're going to be looking at over several lectures now. So this is the thylakoid membrane again, but they've drawn it in a way so it's easy for us to talk about how this process happens. But remember, this isn't how it's laid out in the actual thylakoid membrane. It's not so nice and precise. All right, but for ease of talking about it, this is how we like to visualize it. And so here we're looking at the thylakoid membrane, and then what you see toward the bottom of the figure, that's the lumen. So if you cut open the thylakoid membrane and peer inside, that's the lumen. And then what you see on the top portion here, that's the watery portion of the chloroplast, the stroma. Okay, so you have the lumen side of the thylakoid membrane, the stroma side. Okay, so we'll be referring to those. And then you're seeing the 4 big transmembrane complexes, photosystem 2, cytochrome B6F, photosystem 1, and ATP synthase. And then you see that there's some other things going on in this image too, right, that are smaller. You see water over here in the lumen. So water with the photosystem 2 has that fantastic ability to split or extract electrons from water, oxidize water. And with both photosystems, you have the chlorophyll in the reaction center, its electron getting excited when light energy strikes it. Okay, so let's see, I think this is the same image just from the next edition. So it's the same thing. It's a little bit bigger. I like this one, a little bit brighter. Same thing. Okay, so we're going to talk about this process starting from photosystem 2. And the level of detail I'm covering in lecture is what I expect for learning this material for the exam. So it's more than what you can typically find on YouTube videos. I've had students try to use YouTube videos, and they're not as detailed as what we cover. So just be aware of that. What we cover in lecture, my recorded lectures, remember that's a resource. What we're covering, make sure that you get to that level of detail. All right, so let's think about it from photosystem 2. So imagine the antenna systems capturing that light energy using inductive resonance, funneling it to the reaction center, photosystem 2. Then a chlorophyll pigment in photosystem 2 is going to get excited by that light energy. And the way we denote that in written form is we say P680, we're going to say that's the chlorophyll in the reaction center. Okay? And P stands for pigment. All right, so P680 for photosystem. If you put the asterisk, you're telling me that that electron is in the excited state now. All right, so P680 asterisk means you understand that that chlorophyll in the reaction center, its electron got excited and it got boosted to a higher energy state. Hopefully it gets into the triplet state, because then it'll stay around long enough for the next phase to take place. So again, we've seen this already, just refreshing your memory, this idea of the excitation of the electron, getting it boosted to a higher energy state, and now it's ready and poised, ready to go. It needs to get given off to an acceptor molecule. So what's going to happen is the acceptor molecule is called pheophytin, which you can abbreviate to pheo. All right, so you don't have to write it all the way out. Okay, so pheophytin is a modified chlorophyll molecule. Okay, so pheophytin is going to be the acceptor molecule. So the chlorophyll in the reaction center says, hey, pheophytin, I'm going to give you that electron. And then you would denote it this way. So if you write it P680 plus, pheo minus, what you're telling me is that you understand that the chlorophyll lost, donated off the electron, pheophytin got it. All right, so now plus because it's missing an electron, pheo is minus because it gained that electron.
That electron, that was came from.
Yeah, we'll get into that. We're going to piece this all together. But yes, ultimately it's water is the donor of the electrons. So we say that this is a charge separation because the chlorophyll is missing an electron, Theo gained one. So we say that's a charge separation. And this is the point where you say, okay, this is the point where light energy has now been converted into chemical energy, into this charge separation, this redox reaction. Okay, so this is the first redox reaction moving forward. Okay. Yeah. So this is photosystem 2. And again, just trying to impress on you that it's a massive transmembrane complex. Let me point out over here, the OEC that you see off to the right and is pointing in this area. That's the oxygen evolving complex. All right. Where is it, this one? Oh, maybe it's the not. No, that's not a very good image of it either. Okay, so just let's go back to the big picture. So the chlorophyll in the reaction center, and then we need to think also now about the oxygen evolving complex, because that's going to also be, light energy is going to be allowing for the oxygen evolving complex to do its job. All right, so we need to think about that. So that chlorophyll in photosystem 2 in the reaction center is like, okay, I just donated off an electron. I'm missing an electron. I'm not happy. I want my full complement of electrons. And so the oxygen evolving complex part of photosystem 2 is going to extract electrons off of water. So water is our ultimate electron donor. So it strips off, it splits, it extracts, it oxidizes, however you want to say it. And so basically what's happening in the oxygen evolving complex is water is getting oxidized. And when you do that, you will eventually end up with molecular oxygen, O2, plus electrons, of course, are getting taken off of water. And then protons are also left over. So for our purposes of talking about the light reactions, we really don't say much more about oxygen. That's like, okay, yeah, whatever. It's not really involved in the light reactions, it's just a product. However, the protons and the electrons, those are very important as we talk about this process of the light reaction. So the water, an electron gets oxidized off water, and that will be given to the chlorophyll in the reaction center that just donated off an electron. So now, you know, that chlorophyll says, okay, I need that electron. And now it's back to its full complement of electrons and it's ready to get hit with light energy again. And so this is happening at nano and picosecond time intervals. It's very, very rapid. And the taking of electrons off of water is very, very rapid. Another big payoff of getting water oxidized is the protons that will start to build up. So those are building up in the lumen. So we often talk about how they're being dumped into the lumen. I tend to say that a lot. So they're starting to build up in the lumen every time you see water getting oxidized, getting those electrons stripped off of it. So that image on the bottom right here is trying to show this idea. So this is part of photosystem 2. And they're saying that it's in that region of photosystem 2 in the OEC that you have the electron getting stripped off water, that chlorophyll in the reaction center gets it, and now it's like, okay, now I can get hit again with light energy. So that's all happening here. The way they drew it, it makes it look like it's a, you know, a totally separate entity, but it's not. It's all happening in photosystem 2. Okay, it's just a slightly different region of photosystem 2 where the water gets acted on. Okay, so we're still zooming in this region. And here they are showing how the protons are showing up in the lumen of the thylakoid membrane. So this blue electron now in photosystem 2, that's the one that's getting donated off to pheophytin. So you have to imagine, they don't draw pheophytin here, but you have to imagine pheophytin is right in this region, accepting that electron. So now pheophytin has to do its job, which is to pass that electron to the next player. and that will be a plastoquinone, which you can just abbreviate PQ. You don't have to write it all the way out. So these PQs, they're hanging out, bound or attached to photosystem 2. So they're right there, and they're like, okay, give me an electron. I'm waiting for the electron. And when that happens, that first plastoquinone will get the electron. What happens is then it immediately, that first plastoquinone turns to a second plastoquinone and donates the electron to the second plastoquinone. So it's a boom, boom, you know, first plastoquinone, second plastoquinone. Well, the thing about plastoquinone is in order for plastoquinone to be chemically happy, so to speak, it needs 2 electrons. So it's only the second plastoquinone, so far, it's only received 1 electron. And it's like, no, I'm greedy. I need another one. And so what's going to happen is everything repeats. And when I say everything repeats, we go all the way back to light energy striking photosystem 2, that chlorophyll electron getting excited, passing off to pheophytin. Then the chlorophyll reaction center pigment turns to water and says, give me an electron. So all of that has to happen again to get another electron, a second electron being given to that second plastoquinone. When that second plastoquinone gets its 2 electrons, then it will grab 2 protons from the stroma. It's important you understand where those protons are coming from because it's important in what's going to be set up here. Okay, so plastoquinone says, okay, I've got 1 electron, give me another one. So it repeats, it gets its second electron, and now it's like, okay, now I need 2 protons to be chemically stable and happy, and then I'm good. So they're going to grab 2 protons from the stroma. So now 2 protons have disappeared, so to speak, from the stroma. They become attached to the plastoquinone, and that's important to think about. When you write it like this, PQH2, that denotes that that second plastoquinone has 2 electrons and it grabbed 2 protons. PQH2, it's fully reduced, ready to go. Now in that state, it's ready to do its job. And it has to deliver electrons to the next player in the game. Okay. So we call that a 2 electron gate because I like to think about, since I like horses, I think about thoroughbred racing where they're in the gate and the horse isn't going to get released until it gets 2 electrons. All right. And so if that imagery helps you, so PQ isn't going to come out of the gate until it has 2 electrons, 2 protons. So here in visual is what we just talked about, where you have that plastoquinone. And here you can see in figure B that what they did is they took this tail, the side chain, and they replaced it with the letter R. So it's just easier visually. So figure B, you see 1 electron coming in, and they put it as PQ dot minus. That just means it's semi-reduced. It's like halfway there, not quite. And then you see another electron coming, plus 2 protons, and now it's fully reduced. PQH2. Yeah, in that state, you could think of it as a free radical. It's very reactive and unbalanced, so to speak. So here, we're going to see that PQH2 is very important as a mobile carrier. It's a small molecule. What we just saw on the previous slide, it's not very big. Okay, it's a very small molecule. So it's easily mobile in the thylakoid membrane. So it actually disassociates off of photosystem 2 and it starts to move laterally through the hydrophobic portion of the thylakoid membrane. All right, so it's out of the gate and now it's moving down the track and it needs to reach the next player in the game. So I literally need you to know that it's moving laterally in the hydrophobic portion of the membrane. I need that level of detail. In the membrane means it's right in the hydrophobic portion. And it's moving along down the track until it can bump into the next player, which is cytochrome B6F. So that's one of the massive transmembrane complexes involved. Okay, so it gets to the cytochrome B6F and it is special of what's going to happen next. what we see is that both of the electrons that it got will be delivered, but in different pathways. And so we're going to see that one electron is going to get passed to the next player in the game, iron sulfide portion of cytochrome B6F. And then I just put arrow, arrow, eventually it'll go, that electron gets all the way down to photosystem 1. So that's one pathway. The other pathway, we call that pathway the linear pathway. The other pathway that plastoquinone is going to give off the electron, and it's going to go to a cytochrome B within that cytochrome B6F complex. That pathway is what we refer to as the Q cycle, because we're going to see that it does this circular route or pathway. Yeah, if you hang with me here, let's see. I'm going to show you some visuals too, so hopefully this will help. So we're going to hold off on the second bullet point. We'll get to that eventually. I want to talk a little bit more about the Q cycle before we get into finishing off the linear path. So again, here we're looking at PQH2 here. You can see on the left, it's in the thylakoid membrane in the hydrophobic portion, and it's getting to the cytochrome B6F. And they're trying to show in this drawing how one electron goes one route, one electron goes the other route. Okay, so again, just trying to give you a visual of the electrons that are splitting into two different routes and all the pretty colors. So here is another way to look at it in more artificial drawing. So you see the fully reduced plastohydroquinone dissociates from photosystem 2. It moves laterally through the membrane, bumps into cytochrome B6F, and you can see one electron gets given to the iron sulfide. And then eventually you're going to end up at photosystem 1. And then the other electron stays in the cytochrome B6F complex. This is the top electron here going off to cytochrome B. This whole thing is what we call the Q cycle. All right, so we're going to talk about that next. So we're going to zoom into what's going on in this portion here. Correct. Yep. All right. So you can see here that, that first cytochrome B got the electron, and then you see the next player in the game is another cytochrome B. So that electron goes from cytochrome B to cytochrome B, and then there's a plastoquinone sitting in the cytochrome B6F as well. So what you're seeing here with this first run, this plastoquinone comes and bumps and donates both its electrons. You see cytochrome B, plastoquinone. Well, okay, it's the same kind of plastoquinone that we already talked about. That plastoquinone is not happy with just one electron. Okay, it's unstable. It's not going to be able to do its job. So what we see here in the Q cycle is that PQH2 that came off of photosystem 2 is going to donate to cytochrome B, which will quickly donate to another cytochrome B, and then to that plastoquinone. And then again, you can write it, Q dot or Q dot minus. Then all of that has to happen again, because that plastoquinone is greedy for electrons. It's like, no, I want 2 electrons, or I'm not going to do the next thing. Okay, so when I say repeat, I'm talking repeat all the way back to light energy striking photosystem 2. All right, so because what we have to have happening, we have to have another PQH2 moving along and bumping into the same cytochrome B6F. And in order to get another PQH2 to come along, we have to have everything back in photosystem 2 happening again. So you have to imagine, again, light energy striking, photosystem 2, that chlorophyll in the reaction center, its electron gets donated to pheophytin, who gives it to plastoquinone 1, who gives it to plastoquinone 2. And then that plastoquinone is like, hey, I need another one. So then it repeats. And then that plastoquinone, the second electron, grabs 2 protons. Now a second plastoquinone out of the gate, run down the track, and give that a second electron into the Q cycle. So there's a lot of, repeating back from the beginning and then going forward. That kind of makes sense. All right, so that PQ then, that's in the Q cycle, it's going to get a second electron, but it also needs 2 protons. In order for PQ to be fully chemically, happy and ready to go, it needs 2 electrons, 2 protons. So that PQ in the cytochrome B6F, again, is going to grab protons from the stroma. So again, we see protons disappearing from the stroma, 3 protons disappearing. Then once that PQH2 or the plastoquinone in the cytochrome B6F, once it gets that second electron, it grabs its 2 protons, then they see that it releases from the cytochrome B6F, but at that point, it's really hard to track what happens to it next. And every year, at any conference I go to, I always try to pick the brain or go to a seminar, and they still haven't quite figured out how to figure out what happens to that PQH2. The current thought is it gets involved in the light reactions in different areas of the thylakoid. But anyway, for our purposes, what you can say is that this PQH2, part of the cytochrome B6F, it's released, and we're not quite sure what happens next to that PQH2. So the fact that this PQH2 is playing a role kind of in 2 different spots, right? So there's one PQH2 that's associated with photosystem 2, and then there's another one with the Q cycle in the cytochrome B6F. And in both cases, they have to have 2 electrons and they grab 2 protons from the stroma. So what you see happening is 3 protons are disappearing from the stroma as water is dumping protons into the lumen. So now if you start thinking about it, you're like, okay, protons are disappearing from the stroma. They're showing up. Yeah, they're increasing in the lumen. So now we have a gradient. We have a proton gradient across that thylakoid membrane. Anytime you hear that phrase, a proton gradient across a membrane, you should immediately start thinking about, ooh, that's good potential energy. Now that cell can do something with that when you have a proton gradient. All right, so a proton gradient is potential energy ready to do something. So we have to hang on to that thought. So what they tend to say is that because the protons are disappearing from the stroma because the plastoquinone is grabbing them, and because they're building up in the lumen, what we're saying is that they tend to say, well, that increases the number of protons that are pumped. So what they're trying to say here, pumped across the membrane from the stroma to the lumen. Oh, I forgot this part too. So not only is water getting stripped of electrons and protons are building up, but right here, I forgot to finish this thought. When that plastohydroquinone that's coming from photosystem 2 reaches cytochrome B6F, donates 1 electron one way, 1 electron the other way, and then it dumps its proton. Because if it's going to lose 2 electrons, it's got to give off 2 protons to be chemically okay. All right. And so that's what they're referring to as being dumped. So they have protons being dumped, so to speak, because this PQ grabbed protons from the stroma and now has transferred them into the lumen. So they say that it's a way to pump or dump the protons across the membrane into the lumen. So what that's doing is, as you get the protons disappearing from the stroma because they're reacting with the plastohydroquinones, and then you get the protons building up, that's what they refer to as, you get that electrochemical gradient established. I tend to say proton gradient because we're zooming in on protons and not some other cation. So if you look at the light reactions and you say, okay, this Q cycle is weird. Like, why don't they just keep the electrons flowing linearly all the time? Just do that. But if you mentally take away the Q cycle, you get less proton pumping. So that means you get less of a proton gradient, which means you get less potential energy. So having that Q cycle doing its thing during the light reactions is actually creating a better situation where you get a better proton gradient. And that's going to become important as we think through this. Okay, so this is the second run at getting this plastoquinone that's semi-reduced in the cytochrome B6F. So now they're saying a second PQH2 is going to come along, dump its electrons. You know, one goes linear, one goes into the Q cycle. So now that semi-reduced PQ gets another electron, grabs 2 protons, and then it releases. So again, protons disappearing from the stroma, protons building up in the lumen. So this Q cycle is a little weird, but it's effective at its job, which is really developing a proton gradient. Yes, so this other electron we haven't talked about yet, but now we have to follow what's happening to these electrons as they're going. We say that the electron that gets given to the iron sulfide, we say that's the linear route of electron flow. So we have to think about that. But first here, so these 2 slides that I've been showing you, I put them on one here for study purposes. So we just went over this. It's just now they're on both. Both of them are on one slide. Yes. You got it. Yep. So this is the first PQH2 coming off of A, one goes to iron sulfide, one goes to P, and then it drops. And then everything repeats. So you get a second PQH2 coming. The electrons into both those routes. And now this semi-reduced plastoquinone gets the second electron, grabs the 2 protons, releases. So it's an effective way to increase the amount of protons that get transferred from stroma to lumen. It increases the proton gradient. You get a nicer, steeper proton gradient. Yes. Yeah, and that might be happening. Yeah, good thought. Exactly. And I talked to the experts that study this stuff at the conferences, and they still, I think it's just really hard to experimentally label them differently. You know, it's like, how do you label them differently? And so I think they're just making some assumptions, good assumptions, but yeah. Okay, so let's think about the linear flow here. So that PQH2 releases from photosystem 2, moves laterally through the hydrophobic portion of the membrane, gives one of its electrons to iron sulfide, and then that will give it to the cytochrome F. Then cytochrome F turns around and gives the electron to plastocyanin. Again, you can just abbreviate everything. PC is fine for plastocyanin. It's a protein. Okay, so PC is important because it's another mobile carrier. So plastoquinone, PQH2 is a mobile carrier. PC is a mobile carrier. When you look at where it's located, it's actually attached or associated with the thylakoid membrane on the lumen side. Okay, so it's on the lumen side. In this one, when I'm always imagining this, have you ever been on those roller coasters where you hang below the track? You've actually done that? Has anyone actually done that one? The ones that where instead of sitting on the track, the car, yeah, the car suspends and your legs dangle. That, yeah, yeah, I'm getting goosebumps. Like, no, that freaks me out. So if you've done that, kudos to any of you, because that freaks me out. But that's what I imagine plastocyanin doing. It's like, I'm going along the you know, the railroad or the roller coaster track. So what it's going to do is it's going to grab that electron, and so it's kind of like, associated with cytochrome B6F. It's like, okay, I'm waiting my turn. So it's like at the start of the roller coaster, and then it gets the electron and then it releases off and goes along the lumen side of the thylakoid membrane, kind of like those roller coasters. So that iron sulfur, if anyone's curious, I've had students ask, what is the iron sulfur? It's called the Rieske, so they often label it FESR. The R stands for Rieske. It's just the gentleman, the scientist who came, fully got this all mapped out. So you don't need to know that. It's just some students have asked in the past, what's an iron sulfur protein? So that's what it looks like. Okay, so what we just described is this electron going from the iron sulfur to cytochrome F, and then the plastocyanin on the lumen portion of the thylakoid membrane. Okay, and so now it cranks along until it can do its job, which is to make a delivery to photosystem 1. So both photosystems need to get hit with light energy for this process to keep cooking along. If photosystem 1 doesn't get hit with light energy, then plastocyanin can't do its job, because what has to happen is photosystem 1's chlorophyll has to lose an electron. So it has to get hit with light energy, get excited, give off the electron to an acceptor. It's not showing here yet. And then plastocyanin can say, oh, you're missing an electron? Well, here you are. I'll give you one. All right. So here, again, putting that in the whole image here, you see the plastocyanin move you off cytochrome B6F and getting to photosystem 1 have to have light energy striking photosystem 1 as well as photosystem 2, and it needs to be done in concert. If these get too out of whack with each other, it screws things up. We'll talk a little bit more about that later. Okay, so let's think about plastocyanin. So it's zinging along the lumen portion of the thylakoid membrane. And then photosystem 1 is going to get hit with light energy. That chlorophyll in the reaction center gets excited. So we denote that as P700 asterisk. So that's photosystem 1's chlorophyll. And then that excited electron, hopefully, is going to get donated off to an acceptor. And again, then we say, if that happens, then that chlorophyll is missing an electron. So it's P700 plus. That's how you would write it. Now, plastocyanin can come along and do its job, which is to give an electron to that chlorophyll in the reaction center.
So that's pretty much, if it doesn't have that electron, it's always either piece
Yeah. So with the P700 plus, that means that, okay, I have a missing electron, I got to get it from plastocyanin. And so once that light energy, excites off that electron, gets that electron given off to the acceptor molecule, we're going to zoom in now to photosystem 1. It's a massive complex, transmembrane complex. So the next slide is going to get into the details of what's happening in that complex. So I say on this, a series of molecules. Now we're going to go through what those molecules are. And again, these are all abbreviated. You don't have to spell them all out. So here are the players in the game within photosystem 1. So the first acceptor is another chlorophyll molecule that they denote A0. So you can just say A0 is the next player. That's the one that gets the excited electron from the reaction center chlorophyll. Then A0 gives it to A1, which is a phyloquinone, which is actually vitamin K, if you think about it. Then it gets given to an iron sulfur protein, which they've labeled iron sulfur X. Then it gets passed to another iron sulfur, so they had to give it a special different name, so they say A, and then one more, iron sulfur B. So there's 3 iron sulfur molecules, boom, boom, boom. All right, so that electron that's excited in the reaction center gets given off to A0, who then gives it to A1, who then gives it to X, and to A, and And that's all within photosystem 1. So this next image is putting it kind of into a visual. So they're trying to show this light energy striking the chlorophyll in the reaction center. And then you're seeing the electron flow from A0 to A1 to iron sulfur X. A and B. Okay. Now iron sulfur B is going to be passing it off to this grayish looking molecule called ferredoxin. Yep. So ferredoxin is another mobile carrier. And it's associated with photosystem 1, but it's on the stroma side. Remember, it's a photosystem 1's transmembrane. So part of it sticks off into the stroma. And so the ferredoxin docks there. It's like, okay, I'm ready whenever you can, give me an electron, okay? And so ferredoxin will get that electron, and as soon as it does, it will disassociate off photosystem 1 and start moving around in the stroma because it has to find one more player in the game. That's crucial. And remember, ferredoxin, energetically speaking, ferredoxin is really happy to donate electrons to whoever's around. So hopefully the right players are in place. Okay, otherwise ferredoxin might give the electron to something else. But if we're focusing in on the electron, on the light reactions, the electron transport chain, there's a very particular player. Okay, so ferredoxin gets that electron. It disassociates or comes off of photosystem 1, and it's in the stroma. It's mobile, so it's going to start moving around, and hopefully it's going to bump into this other molecule called FNR, which it used to be in previous publications or textbooks, they used to call it a flavoprotein, but actually FNR is a better way to talk about it because it's more descriptive of what it actually does. So FNR stands for ferredoxin, NADP, and then the R stands for reductase. So what this is doing is it's trying to say that the FNR takes an electron from ferredoxin and it's going to give it to NADP+. So this FNR is an enzyme in the stroma, and hopefully ferredoxin is going to bump into it. They'll get that exchange of electrons, and then that FNR enzyme will then give that to NADP+. Important that you put plus. NADP+ is the final electron acceptor, not NADP, not NADPH. So when you say plus, you're saying you understand that it's missing an electron. It's ready to accept an electron. So NADP+ is the last player in the light reaction game. It'll take that electron and become fully reduced to NADPH. And that is one huge goal of the game. So if through the light reactions you can get this electron flow happening where you ultimately get NADPH being made, that's how you win. How you win the game. This is showing, if you've not thought about NADP much at all lately, this is what it would look like. I'm not going to ask you details about it, but I've just had students in the past say, what is that again? So if this helps you as you're studying, and then they're just showing how the trans electrons used. They're actually showing you where they end up. So you have a chemistry mind, and that helps you work through this NADP+ to NADPH. Okay. All right. So we've worked through from start to finish the electron transport chain process. It's complicated. I remember sitting there learning it for the first time. It's like, what the heck? It's complicated. So if you're sitting here going, what? I get it. I was like that too. But that leads me to say that means you got to spend some time going through this. All right. So when you're studying, and the way I learned it, I created a silly story in my head, like the roller coaster thing. I mean, that's what I I get really weird with how I learn. You know, I try to get really fantastic or silly or humorous, and that sticks in my head so much better than just memorizing a bunch of dry facts. Turn it into a story. I think all of us kind of intuitively know that stories are much easier to remember than someone just spitting a bunch of facts at you. I mean, even when you're a kid, you can remember stories, but someone just spitting facts at you. All right, so I've seen students do this. It's not just me. I'm not just some weird person. I see other people do this and it works. I mean, I had students that were working in my research lab that were taking this class, and 3 weeks after the exam on the light reactions, we were in the lab and we were chatting, and I said, "Hey, do you remember the light reactions?" And they had it from start to finish, but they turned it into a story, and it just stuck with them. So I really, really encourage you to embrace that idea of getting silly or creative in how you either visualize this or create a story, and it'll fall into place that much quicker and easier and stick with you. Okay, one more idea really quick, and then we're going to talk about it again next week. As all of this is happening, there is this proton situation going on, right? So we said that with the help of PQ and the T cycle, you get protons disappearing from the stroma. You have them showing up in the lumen. So you get this proton gradient. So that's another key thing of what's happening here. Anytime you hear, oh, there's an electron transport chain going on, anytime you hear that, you should immediately go, oh, I bet there's a proton gradient developing, because that's really one of the jobs of the electron transport chain. As the electron transport chain is going, yes, you get that lovely NADPH, that's great, but the other thing this is allowing to happen is allowing a proton gradient to establish. There's some key steps in this process that has enough free energy that can allow for this development of a proton gradient. And so now the protons are going to want to diffuse back to even out their concentration gradient, but they can't go through the membrane because they're charged, so they go through the ATP synthase. And as they're flowing through that, it actually creates a torque force. These subunits actually rotate, and it allows for the ADP and the inorganic phosphate to react with each other. And so that electron transport chain, you get a proton gradient during that process. And that's wonderful because that allows, in this case, the second goal of the light reactions is to get your ATP. Yeah, so here the ADP and the inorganic phosphate are reacting with each other, and that will get you your ATP. So by the end of the light reactions, the electron flow has allowed for NADP to get an electron and get reduced to NADPH. So that's good, but it's also allowed for a proton gradient so that these protons can diffuse through the ATP synthase and get your ATP made. And again, that's showing up in the stroma. So both the products of the light reactions are in the stroma, which is good because that stroma is where we're going to zoom in when we look at sugar production, or at least the start. Okay, we're going to review this again on Monday. So it would be great if you look through this a little bit and start creating your own story so that when we cover it again on Monday, it'll be that more effective for you. Okay, so spend some time this weekend looking this over.